So when we finished up last time, I think one of the problems that we had last time, I actually had a mistake in it, a little algebra mistake, has to do with this sign right here. I corrected it on the PDFs, but I didn't correct it in the video, so I wanted to try and correct it now. We might just go through these equations. This would be a good practice and good warm-up for our work today. This first equation here is going around the perimeter of this circuit, or this portion of the circuit here. So I went through this voltage source and I gained 24, so apparently I'm going to take gains as negative, so I have negative 24 at 0. And then I total up all the self terms. So I have 4 ohms for the resistive portion, I have minus J4 ohms for the capacitive, and I have plus J2 ohms for the inductive. So when I put all 3 of those together, I retain the 4 for the resistance, and then I take the minus J4 and the positive J2 and put them together and get minus J2, I1. And then I've got this piece down here that would be 2 times I1 minus I2, because the net current going down through that's I1 minus I2. And that would be, if we didn't have to worry about the mutual inductance, that would be all of the terms. But we do have to worry about the mutual inductance. And this is where our work is. Interestingly enough, that's not where I made the mistake. So oftentimes you still make the mistake in the original circuit analysis or just in algebra. But if we look at this current I2, it was entering the non-dotted terminal over here, right? So what will we be in? Where will be positive and negative? It means that positive will be, it'll be positive at the non-dotted terminal, right? So I can put the positive there, I can put the negative here. So as I went through that, that induced voltage is going to be a gain, just like this 24 volts is a gain. So it becomes negative JI2. We okay on that first equation? Okay. So the problem here, and again I noted it on the PDF with a light highlighted fix, but I wanted to talk about it so that we could get the at least get it recorded that we've corrected this. So going around this one, I have J3 minus J2 and then 3. So I had initially wrote 3 and then minus J. Well, it really should be a plus J, shouldn't it? Okay, because I've got positive 3 and minus 2 should give me a plus J. So make sure that your notes, make sure when you see the video, you get that correct in your mind. That should be a positive J there, I2. Then again, when we talk about this one, we're going to talk about the net current going up. So I'm going to have I2 minus I1. There's I2 minus I1 times 2. And now again, I still have to deal with a mutual term. So this I1, it enters the dotted terminal over here, right? So that means it's going to induce a positive at the dot and negative at the non-dotted terminal. So when I went around there, I had a gain. We treat gains as negative in this equation. So then it was just a simple matter of going through and tidying these up, putting them in matrix form. When I did that, I think I had 3 plus JI2 and 2I2. So this became 5, and this one also needed to be a plus. So those 2 points, make sure that they're correct in your notes. Questions with that? Okay. So I just wanted to go over fixing that one. And again, oftentimes the problems can still lie in the algebra and whatnot. Well, I had shown you this problem. Did anyone download the PDF and try their hand at this?
I
Looked at it? Okay. Okay. So I'm probably not going to do all of these. I'll do at least one of them, and then you can finish it up if you want to. I think there's one of the homework problems that runs you through. I think the homework problem is very similar to this one, and you'll see the solutions on the homework problem, so you can look at that. But let me go ahead and start at this point. Again, I'm going to take drops as positive. Okay, so I'm going to take drops as positive. If I start at this point and start working my way around this circuit, what happens? I have a gain of the voltage V, so I'll say that's minus V, right? And then as I go through this, I've got I1 times R1, so that'll be plus I1 times R1. That gets me over to here. Now what do I have? Plus I1 minus I2. That's the net current going down there, and I'm going to multiply that by J omega L1. Is that right? And then where do I go? So I've got now down to here. I'm going to have then plus I1 minus I3, because that's the net current going down there. And that'll be times J omega L3. And then lastly, I have to finish up with this capacitor, at least for the self terms. I'm a long ways from done. But I'll have positive I1 times 1 over J omega C2. So how many self terms did we say we were going to have? 1, 2, 3, 4, 5. So I think I've got those done. Let me double check those before we go on. Yep, I think we're good with those. So then the fun begins with the mutual terms. So we said that there were going to be 4 mutual terms because the current through here induced a voltage here. Likewise, the current through here induced a voltage there. The current through here induced a voltage here. And finally, the current through there induced a voltage there. So we got 4 of them. So I guess we can just start out. We might start out with the current. And a lot of times what I'll do, I can choose that it's I2 minus I3 or I3 minus I2. Why not make my life kind of easy and say, well, I want to find this current right here because that's going into the dot, right? Okay, so what current is that going to be? Going into the dot, that should be I3 minus I2, shouldn't it? I3 minus I2. And that's the current into that one, so that's going to induce a voltage that is positive at this dot here. So we went from positive to negative, so that's going to be a drop, isn't it? So I can say that I have minus, no, not minus, plus, because we're taking drops as positive, so it's going to go positive and negative, so plus. And then what would the mutual term be? J omega M1. Okay. Now what else will I have here? Well, I've got this I3 minus I2. Why don't I look at this one? That's going to have a voltage here that is, what, positive and negative. So now as I went from that, that's a gain. How do I treat gains? Yeah, so it should be negative, shouldn't it? And that'll be J omega M2. Okay. Then what else do I have here? Why don't I take the current that's going into this one? What current is that? I1 minus I2. So I1 minus I2. And that's going to induce a voltage. That current going into that one is going to induce a voltage over here, isn't it? And that, because it's going into the dot, it will be positive here and negative there. So that is another gain. So we're going to take that as negative. And that'll be J omega M3. And then what do we want? The last one would be the current going into this dot. What's that? I3 minus I1. I3 minus I1 goes into this dot, so that's going to induce a voltage that is positive here and negative there, so that's a drop. We'll take that as positive, and that will be J omega M3 also. So I think that's all of them. Did we get all the mutual terms? We said there'd be 4. There should be 4, shouldn't there? Let me double check these, and I'll probably talk a little bit about them. Okay, so I think these are correct. Any concerns on them? Let me talk a little bit about them. Let me separate them here and make this last little bit of real estate here. Let me talk about them. I said that, why don't we make life easy and say that this current goes into this dot. There's no requirement that we do this. I mean, we could take the current going the other way, in which case I would have I2 minus I3, wouldn't I? So I2 minus I3 is going into the non-dotted terminal. So the non-dotted terminal becomes positive, right? So I'd have something like this. That would be positive and that would be negative. So I came around there and that's a gain. How do I treat gains? Negative. Negative J omega M1. So are these two terms that I have above each other the same? Yeah, absolutely. When I factor that negative sign through, I get exactly the same thing as above. So if you do this by the rules, if you do this correctly, you may have different signs, but when you really look at the terms, they should be the same. Yes? I didn't include the first capacitor. This one, is this the first capacitor? Okay, so why didn't I include that guy? Because I'm going around this one. Okay. I spent too much time in a playpen as a child. I just stay right in this one here, right? Okay. Other questions? Do you want to go over and do loop 2? Okay. So I got some clean real estate here. I won't belabor this. We won't do 3, but let's go ahead and do 2. I think I can do it this way. Okay, well maybe I'll ask you, do you want to do 2 or 3? I'm not going to do both of them, but I'll do one or the other. Is 2 okay? Everyone seems to be pretty hot on this capacitor, so let's do 2. So again, loop 2, we're going to take drops as positive. So let's go. I guess we've got this kind of laid out for loop 2. We're expecting 3 self terms and 4 mutual terms. So if I start up here and work my way around, I've got a I2 times what? 1 over j omega C1. And then moving around here like this, I'm going to have I2 minus I3 times what? J omega L2. I2 minus I3. And then finally I will have I2 minus I1 times J omega L1. That gets me back to the starting point. So those are the self terms, right? I was expecting 3. I've got 3. Let me double check that before we move on. Okay, I think we're good. So now we got the mutual terms, right? What are the mutual terms going to be if we just survey this thing roughly? I would have a current through this one inducing a voltage here. I would have the current conversely in this one inducing a voltage here. I would have the current through this one inducing a voltage here. And finally the current through this one inducing a voltage there. So maybe I'll come down and do this one first. Why don't I go ahead and look at this current going into the dot. So I'll talk about I3 minus I1. Isn't that this current here? I3 minus I1. And that's going to induce a voltage here that is positive and negative. So when I went around, that was a gain. So I'll say that that is minus. And that would be J omega M2. Now also, with this current that's entering the dot, it induces a voltage up here that's positive at that dot and negative. So I went around, that was also a gain. So minus I3 minus I1 times this time J omega M3. Good so far? So now we just have to do the business with this j omega m1. Everything else is going to have a j omega m1 in it. So let's talk about the current going into this dot. We could talk about I1 minus I2, I1 minus I2. That'll be j omega m1. That goes into this dot, so it's inducing a voltage here that is positive. So that was a gain, so that should be negative. And finally, I will have the current into this dot, which is I3 minus I2 times j omega m1. That I3 minus I2, that was going into that dot, so that's making this positive and negative, so that's another gain, so I treat gains as negative. Kirchhoff says that's equal to 0. Did we get 4 of the mutual terms? 1, 2, 3, 4. Yeah, we did. Let me double check those. I think we're okay. Questions with that? I mean, let me separate this. Could we have done this differently? I mean, let's put our, let's look at one of these here. Let's say that instead of going into this dot, we'd come out of this dot, so we say that we have I1 minus I3. That's going this way, isn't it? I1 minus I3. So that's going to induce a voltage, for instance, in this one, that's going to be positive at the non-dotted terminal. Starting to get a lot of marks there, but we'll say that's positive there. So as we went around, we went from positive to negative. That's a drop. We took drops as positive. Is that the same thing that we had the term above it? Yeah, it is. When you factor that negative sign through, it's exactly the same. One time when we had a smaller class, I had about a dozen students. We had a game of this and put it up on the board. And one student would come and write the current, and then the next student had to come and write this with the sign. Okay, you can do it. You have to think about it, right? Because if someone writes this, you're going to have to put the negative sign out here, whereas if someone writes that, then you don't have a negative sign, do you? So I'll spare you that game. Yeah, it's fun. So questions with that? No questions with that. What's that? You want to play that game? Yeah. So. Well, I think you've got a homework problem that'll take you through one more loop on this, so I'll leave it at that. Well, up until now, we've looked at mutual inductance with the M term, j omega m, of course, where m was a product of self-inductance and the coefficient of coupling. Maybe some of you in the past have dealt with mutual inductance and you used a 2-to-1 or something like that, a turns ratio, maybe it was described as. So we want to talk about that. And if you have a high efficiency transformer, usually an iron core transformer, you can usually just look at the turns ratio. And I've got a table here. I realize that this table is probably a little bit hard to see on the video, but I'll put it up also on the website. And if you happened onto this video from some other place, I'll put in the description of this video, I'll put a link to that website so you can go and get this chart. And if you need this chart on a final or something like that, I will make sure that I provide it to you. But what this gives you is based on your turns ratio, and really all this is, this indicates an iron core, which is going to be a high efficiency transformer. And based on different dot arrangements and different polarities of your input and output, or your primary and secondary voltage, or your input and output current, or primary or secondary currents, you have the relationships between those currents based on the dots and the directions and the polarity and so forth. So I wanted to use this, and we'll come back and look at this. I wanted to use this to look at a different type of problem and see if we could tackle it. So let's look at this problem here, where we have the circuit given with a voltage source, and then I have some mutual inductance. I've got a 2-to-1 ratio. Now that doesn't necessarily mean that there are 2 turns here and 1 turn there. That'd be a really inefficient transformer. But maybe there's 200 or 2,000 turns here and 100 or 1,000 turns over here. And maybe I assume some currents, I assume some voltages. I was given the dots. We talked about how you could do that upon inspection, but I was given where those dots were. We've got this resistor over here acting like a load, and we'd like to find I1, I2, V1, and V2. So let's see if we can do that. So as I work my way through here, I'm going to come up with some equations. Let me look at Kirchhoff's voltage law. Let's see, but yeah, Kirchhoff's voltage law for the loops. And what would that look like? If I looked here and I started here and I went around, I would have a gain. So I'm going to take gains as negative. So I'm going to say that I have minus 10 at 30. So that will put me up to that point. And then I'm going to have a drop as I go through that resistor. I'm going to take drops as positive. So I'll have a positive 1 ohm times I1. And that gets me to this point. And the way we usually handle this is with this assumed voltage here. I'm going to be going, this is V1, that's the voltage at this point with respect to that point. So as I go from positive to negative, that's also a drop. So I will add to this, add V1, because that's a drop. That gets me back down to here, and Kirchhoff says that's equal to 0. Now, as far as equations go, like say this is my first equation, I have a bit of a mess. I mean, I have how many unknowns? I have 1 unknown, 2 unknowns. So let's say that I've got equations. Keep track of this over here. Not examples, but equations. And unknowns. So how am I doing? I got 1 equation and I have 2 unknowns. So I need to keep going. More equations. Hopefully less unknowns. So with the second equation, I'll go around this loop here. So what I'm going to do is, if I start right at this point, I'm going to have a gain. So I'm going to take minus V2, because I go from negative to positive. So minus V2. That would be a gain. And then I have a drop, so I'll take positive 2 ohms. There's 2 ohms times this I2. That gets me back to my starting point, and I could say that that's equal to 0. So I've got now 2 equations, but I added 2 more unknowns. So I've got 4 unknowns. So not going real well so far. And those of you that are comfortable with the examples that we did before, you might be wondering, well, didn't we need to talk about j omega L or j omega M dealing with the self-inductance and the mutual inductance? Well, we're going to lump that all into V1 or V2. So at this point, I need some more help. So I'm going to go to my table here and see if I can get some help from that. So let's look at this table. If I want to talk about the voltage, so when you look at this table, the top 4 examples are voltage. The bottom 4 examples are current. You notice the equations for voltage is N1 over N2, N1 over N2, there's a negative sign there, so be careful of that negative sign. And then when you go to the currents, it's the opposite ratio, N2 over N1, N2 over N1, and again you have that negative sign there. And that's probably pretty hard to see on the video. It'd be a little easier to see on the PDF, and like I say, is up on the website, so you could print this out and keep it as you work through homework problems and things like that. Well, let's look at the voltage. What do we have? I've got V1 that's positive and negative, so all of these are candidates in terms of the polarity of V1 and V2. But the dots here, I have a dot in the upper position here and the lower position there. So I'm not going to use this one. I'm not going to use that one. Let's see, this one's in the upper position, this one's in the lower position. I think this is my ticket right here. So I'm going to then say with equation number 3 that I have, what's this, V1 over V2 is equal to minus N1 over N2. So minus N1 over N2, what's that going to be? Well, N1 is 2, so I have minus 2 over 1. Okay, that comes from minus N1 over N2, where this was, of course, N1, and this is N2. So how did I do on my equations? I've got now 3 equations, and what? Still 4 unknowns, right? V1 and V2, I've had those for a while. And this is just showing you where this comes from. Let's, N1 and N2, we're not going to count those as unknowns. We know what those are. Well, let's see, if I can get one more equation and not introduce any more unknowns, I'm good to go, right? So let's see if we can do that, a 4th equation. So I'm going to look at the currents here and see if I can make the currents work out. Let's see, what do I have? I've got I1 going to the right and I2 going to the right. And then the dots are opposite. Let's see, the dots are the same here. The dots are opposite here, but I2, let's see, it looks like I don't see anything that fits. I1, I2, they're both on the bottom, both on the top. I definitely don't like those. This one's probably the closest. The dot is in the upper position here, it's in the lower position here. The only thing that is troubling is my I2 is opposite here, isn't it? So what I think I will do is this one would be what? I'm just rewriting this over here so it's a little easier to see. I1 over I2 is equal to N2 over N1. Well, if my I2 is opposite, because my I2 is going to the right here, and here it was assumed going to the left, what do? Well, I'll just stick a negative sign on there and make that work out, right? So let me put that up here, properly document that with my equations. I've got then I1 divided by a minus I2, because we agreed we had to put that negative sign in there, is equal to my turns ratio, N2. N2 is equal to 1 divided by N1, which is equal to 2. So I've got I1 over minus I2 is equal to 1/2. Well, how am I doing on my equations and unknowns? I've got now 4 equations and I have 4 unknowns. We should be able to solve this thing. Well, what can I do with this? I could take this equation here. That's going to turn into V1 is equal to minus 2 times V2, isn't it? And then this equation here would give way to something that would probably look like this. I1 is equal to minus 1/2 times I2. And again, we see that relationship. If we're stepping the voltage up, we're dropping the current down. It's a tough world. You don't have any free lunches. So I'm going to take that, let me double check that, yeah, and then substitute that into this expression and that expression. So I won't belabor this, but basically if you solve equations 1 and equations 2 and equations 3 and equations 4 simultaneously or doing some substitutions, I would make those substitutions and then solve them simultaneously. You will come up with the following results, that I1 is equal to 1.11 at an angle of 30 amps, that I2 is equal to minus 2.22 at an angle of 30 amps. Let's see, does that work with that equation? Yeah, that holds that true. If I take I2 and I multiply by minus a half, I get that. Good. So then V1 is equal to 8.88 at 30 volts, and V2 would be equal to minus 4.44 at 30 volts. Let's see, does that hold true with that? I take V2, I multiply it by, minus 2. We come up with that. So you can go ahead and convince yourself of these equations and then solve these equations and make sure that you have those answers. Let me double check those answers for you here so I don't... yes, that's correct. Well, and these two equations here were based on our relationships here. And you've got these in your textbook. I realize that you're probably using different versions of the textbook and things like that. So I won't try and point it out in there. But where it talks about mutual inductance, they have such information. I tried to put it together in a form that I thought was a little easier to use. So this table that I made will be up on the website. And that was key. This table was key in coming up with these relationships and giving us two more equations. So with that, I think we've got that pretty well at hand. We've got another problem to look at, so we'll go on to that. I'd like to look at our last problem today. That's what we call reflected impedance, where we're using maybe a transformer to try and do impedance matching. If you make stereos, you want to drive speakers with amplifiers and whatnot, this might be something that you get into. And maybe I should talk in general over here. Okay. Your author goes through a very similar analysis in the textbook, and this is at the end of chapter 9 in your textbook. But if I look at the at V1, I could say that voltage 1 would be the ratio of the turns N1 over N2 times V2. We saw lots of equations like that on the handout. And likewise, then I would say that I1 would be equal to the inverse of that ratio times I2, right? This is a classic example where if you're stepping the voltage up, you're dropping the current down, right? If you could step the voltage up without dropping the current down, we'd all put one of these on our house, right? That'd save us a lot of power. But you have to take the good with the bad. As we step voltage up, the current goes down. As we step the voltage down, the current goes up. So both those things happen. That's why that ratio is inversed on those two. So I looked at that ratio. I wanted to look at N2 over N1, and I just called that lowercase n there. Your author of the textbook that you have actually calls it A, which is maybe better. Uses an A in there. So now if I talk about the impedance V1 over I1, so I come over here and I talk about a current through here. If I talk about this current I1 and V1, I could say that making the substitution then for V1 and I1 using these terms up here, I would get V2 over N, and then I1 would be I2 times N. So I could say this is V2 over I2 times the quantity 1 over N squared, which V2 and I2, if I talk about V2 and I could put this I2 here, that's really the impedance over here at the load. So that's why I take that and label that Z sub L. So I get the equation that we can use, that the input impedance Z, the impedance that's seen over here with the source, is equal to 1 over N squared, that turns ratio, times the load impedance. So let's see if we can use that equation then to our advantage on this problem. So what's the load impedance on this thing? That'd probably be over here, right? So there's our ZL. That's going to be equal to what? 2 plus J1? Okay. So what's seen at this point, if I look at what's seen at that point and say that that's Zn, I could say then that Zn is going to be equal to what? Using this equation, I'm going to have 1 over n squared. Well, what's n? n2 over n1. So I know that n is equal to n2 over n1. What's n2? That's 2 over 1. So that's 2. N is equal to 2. So n squared is equal to 4. So I could say that I have 1 over 4 times this impedance here, 2 plus J1. So I put that in there. So this turns out to be 0.5 plus J 0.25. So the impedance then seen by the source is going to be equal to what? Well, we have to account for this resistance there, so I could say that that's 1 ohm plus the impedance that is being reflected there, which is our Zn, which is going to be 0.5 plus J 0.25, which we get 1.5 plus J 0.25 ohms. Okay. So you'll hear sometimes people talking about using transformers for impedance matching when they're driving speakers and things like that, or changing from one cable type to another cable type. That's what's going on here. Okay. And like I say, your author will use the symbol A for this. Questions with that? Well, when we get together in the next lecture, what we're going to do is we're going to do one more ideal problem like this. So, like I said, make sure that you bring your worksheet. And then we'll change gears fairly substantially, and we'll start to look at problems where the frequency is changing. I don't know if you've noticed, but all of our problems up to now, we start at 60 cycles, we end at 60 cycles, or we start at 100 cycles and we end at 100 cycles. We're going to start talking about what happens if we have variable frequency on our problems. And that'll lead us nicely into our work for next term. Take care till then.